So this is a walkthrough for problem 3, problem set 2. So you can already see that I've written out 2 iterations of the given instructions. So first you'll want to expand the given instructions into the 3 argument syntax. So this mostly affects instructions like opq, where one register that's listed might be both a source and a destination. So in the first instruction, we don't need to expand anything. There's one source and one destination. And in the second, we can see that it's an opq, and we have 2 sources, R8 and R9. So I'm going to add in an R9 at the end for the destination register. And I'm just going to go ahead and repeat this for AND Q, adding an R11, and XOR Q, adding an R14, and then repeating for the second iteration, adding an R9, an R11, and an R14. So in this first instruction, R8 is a source, as we're reading something from that R8, and R9 is a destination since we are writing to that register. And I'm just going to go ahead and do that for the rest of the instructions. So the second instruction, R8, R9 are sources, and then the second R9 is a destination register. Third, R12 is a source, R8 destination, and so on and so forth. I'm going to go ahead and fast forward through this. Keep in mind that the jump instruction does not take any registers, so we're just leaving it as is. So in all of these instructions, you can see that usually the source comes first and the destination comes second, but don't fall into the trap of thinking that this is always the case. So in this case, R move Q R8 into R9. The R8 is a source, and the R9 is also a source. So even though the R9 comes second, it is still a source as we are using it and reading a value out of it. This also means that you don't have to have a destination register. We've now marked everything as either a source or a destination register. Now we're going to go ahead and mark the first instance that we see every actual register, and then we are going to go ahead and mark every time there is a destination register. So the first one, R8, that's the first time we've seen it, so let's go ahead and mark that. R9, again, first time we've seen that. Now we've seen R8 and R9, but the next one that we see for the first time is R12. We've seen R8, we've seen R9, now we haven't seen R11 before, so we'll mark that one. We haven't seen R10 before, we'll mark that. And we haven't seen R14 before, so we'll go ahead and mark that as well. Now for the rest, the second iteration already has the same register, so we won't be marking any first instances. The next part is to mark everything that is a destination register, so we'll just go ahead and mark anything with a D under it. So now we have successfully set up ourselves for renaming our registers. So this is taking the actual registers that are in the instructions and turning them into physical registers. So I'm going to go ahead and draw a table down at the bottom and list out my actual registers, R8, 9, 10, 11, 12, and 14 on the left, and on the right I'll leave it blank so that I can rename and keep track of my physical registers. Every time you see a marked register, we are going to rename it. So in this first instruction, both R8 and R9 are marked. So we're going to rename R8 as T1. I'm going to make that a note in my table. MR move Q T1. And then R9 we are going to rename to T2, and I'm going to make a note of that also in my table. You might find it helpful to keep a running tally of the numbers that you're using for your physical registers. For the second instruction, we've already seen R8 and R9, and those are not marked, so we will continue to use the renamed registers. So R8 becomes T1 and R9 becomes T2. The second time we see R9, however, it is marked, so we're going to go ahead into our table and cross out the T2 and rename it to T3. So now we have add Q T1, T2, and T3. And you can see the pattern. We're going to rename anything that's marked and use whatever's the latest value in the table for anything that isn't marked. For the second iteration, don't be tempted to simply copy over your renamed registers from the first iteration. The renamed registers for your second iteration are bound to be different from your first iteration, so don't get lazy and keep going through the second iteration. So we finished renaming our registers, which is step 1 of problem 3, and I've rewritten these renamed registers along with their instructions on a new sheet of paper. I've also included these sequence numbers, and these will be helpful and useful when filling out the table. The final step for this problem is to figure out what order these instructions are going to execute in. Because this is an out-of-order superscalar pipeline processor, we don't necessarily have to execute our instructions in order. The second part of that name, the superscalar pipeline processor, means that we have in this case, a dual issue or 2-wide pipeline processor. This means that you can have 2 instructions in the same stage at any given point. Don't think that you can have more, it's a 2-wide. If it were 3-wide, you would be able to put in 3 instructions and so on and so forth. So in this next step, we are going to mark our dependencies, and up to this point, what we've done so far is eliminated 2 out of the 3 kinds of hazards that we commonly run into. We were able to eliminate our write after write hazards, or WA hazards, as well as write after read hazards, or WAR hazards. So in this step, we'll be working around read after write hazards, or raw hazards, with instruction scheduling and data forwarding. So very briefly, a WA, or write after write hazard, occurs when 2 instructions are writing to the same destination. So if the new value happens to be written first, then the old value will overwrite the new value and then cause stale values to propagate. The second, WAR, or write after read hazard, occurs when an instruction writes a new value to a destination before a different instruction can read the old value, the value that it was meant to use. So if this is slightly confusing, this kind of hazard is similar to when you're trying to swap 2 values. You probably store one value in a temporary destination and then copy over the other value into the first destination and then place the temporarily stored value into the second destination. And if you did this without the temporary value, you might end up with 2 destinations that hold the same value instead of swapped values. The final hazard is one that is pretty familiar to us, the raw, or read after write hazard, and this happens when an instruction tries to read a new value from a source that hasn't been updated yet by an older instruction. So we get around this with data forwarding and instruction scheduling. So back to the problem. We're going to mark the data dependencies and mark any instructions that are independent. So I've gone ahead and jumped into instruction number 2, but I will come back to instruction 1 and mark it as independent. The first instruction of a set of instructions will be independent of itself, so you can always mark it as independent. So the second instruction, that T2 value depends on the T2 value computed during the memory stage of the first instruction. So on the right hand side under my dependencies list, I will write 2 depends on 1, and it's a memory to execute forwarding. And this is basically what I'll do for the rest of the instructions. Go down through the list and write arrows from to and from every dependency. So for the third instruction, there aren't any dependencies on previous data, so that is also independent. And here I've accidentally marked instruction 2 as independent, so I'll go ahead and fix that. Instruction 4, the T3 value depends on the T3 value from 2's execute stage. And so I've written 4 depends on 2, and this is an execute to execute forwarding. And it looks like 5 is independent of any previous data. And 6, although it has no registers, the jump is conditional, which means that it depends on the execute stage condition codes from the previous instruction. So here I will just write 6 depends on 5 execute to execute forwarding. So instruction 7, T5 depends on T5 from 3. And so I write 7 depends on 3. And this is a memory to execute forwarding. Next, we look at instruction number 8. And we can see that T5 depends on the T5 from 3. So 8 depends on 3 memory to execute forwarding. Also in that instruction, T11 depends on instruction 7's T11. So that is, again, a memory to execute forwarding. In instruction 9, the T4 does not depend on anything, and the T13 also does not depend on anything. This means we can mark it as an independent instruction. Next instruction, 10, the AND cue. The T12 depends on the T12 from instruction 8, so 10 depends on 8, and this is going to be an execute to execute forwarding. Instruction 11, the T10 depends on instruction 5's T10, so 11 depends on 5, and this is a execute to execute forwarding. And finally, just like before, the jump depends on the execute condition codes from the previous instruction. So 12 depends on 11, and this is again an execute to execute forwarding. So now we will go ahead and figure out the order in which we will execute our instructions. Generally, you want to execute as in order as possible, but independent instructions will always execute first, and you must honor any dependencies. So the first instruction obviously is already given, and it's an independent instruction, so we'll go ahead and cross that off. Now, if we look at instruction number 2, that depends on instruction 1, so we cannot run them in parallel. We'll skip that one. Instruction 3 has no dependencies. It is an independent instruction, so we can run that in parallel with instruction 1. So for the next cycle, we will go back up to the top of the list. Instruction 2 still depends on instruction 1, so we can't run that yet. And instruction 3 has been done. Instruction 4 depends on instruction 2, so we can't do that yet either. Instruction 5 is an independent instruction, so we can go ahead and run that next. Then we go back up to the top of the list, and we say 2, still can't do that. 4, still can't do that either. And now 6 depends on 5, so we still can't do that. Let's look at instruction number 7. 7 depends on 3, and it's a memory to execute, so we can't do that yet. We have to wait one more cycle. Instruction 8 depends on instruction 7, so we also can't do that yet. And instruction 9 is an independent instruction, so we can go ahead and run that in parallel with instruction 5. So far your instructions are 1 and 3, and 5 and 9. And again, we'll run up to the top of the instructions. We take a look at 2, and finally we are able to execute this instruction. We still can't execute 4 since it depends on 2. And then we can look at instruction number 6, and because it is an execute to execute forwarding, we can go ahead and execute instruction 6. So the next cycle will be executing 2 and 6. So let's go ahead and look at the next cycle, back up to the top of the list. We can finally execute instruction number 4 since it is an execute to execute forwarding that depended on instruction 2. And then we'll go down the list and let's look at instruction 7. Instruction 7 depends on instruction 3, and it's an memory to execute, but since 2 cycles have passed, we are able to execute that instruction. So this next cycle is instructions 4 and 7. And if we go back to the top of the list, we've completed everything up to 8. So if you look at instruction number 8, 8 depends on 7, and it is a memory to execute forwarding, so we can't do that yet. We have to wait another cycle. Instruction 10 depends on instruction 8, so we can't execute that yet. We go ahead and look at instruction 11, and 11 depends on instruction 5, but 5 has been done so long ago that there is no issue here. Go back up to the top. 8 still can't be executed yet, and 10 also cannot be executed yet, and 12 cannot be executed either since it depends on 11. Now this is an interesting point. Even though we have a dual issue pipeline processor, sometimes we may not have instructions that we can run in parallel, which means 11 will be going on by itself in this cycle. So going onward, we'll go back up to the top, and we can finally execute instruction 8 since it depends on 7 and 2 cycles have passed. We still can't execute instruction 10 since it depends on instruction 8. So we'll look at instruction number 12, and it can be executed since it is an execute to execute forwarding from instruction 11. So our next cycle will be 8 and 12, and finally our remaining instruction can be executed in this cycle as it depended on instruction number 8. So hopefully you've been following along up to this point, and the order of your instructions should be 1, 3, 5, 9, 2, 6, 4, 7, 11, 8, 12, and 10. Here we'll be filling out the table. That is the second part of problem 3. So now that we've determined the order of the instructions, this part is relatively simple. Just remember that we have a dual issue processor and that write-backs must occur in order. This means that we cannot write back 3 until we've written back 2. So I'm going to go ahead and fill out this table with the E executes and M memory stages. So for instruction 3, we're executing in the same cycle as 1, and I'm writing an M after each execute cycle. And I'm just going down the instructions and doing 2 executes and 2 memories at a time until we get to instruction 11, which, if you remember, was something that was on its own. So we will go ahead and put an execute and memory for that one in its own cycle, and then continue on pairing them until we get to instruction 10, which is on its own because we had a instruction by itself, instruction 11. Now for the writebacks, we will go ahead and look at the sequence number. So 1 has been written back, and then we'll go look at 2. We'll write back 2 as soon as it can be, so in cycle 5 we'll write back 2, and then we'll look at number 3. Instruction 3 can be written back in cycle 5 as well, since it is a dual issue pipeline. I will go ahead and check that off, and repeat the process for the remaining 9 instructions. For this problem, you didn't need to do the forwarding arrows, but if you did, you can easily use the forwarding dependencies list that you generated in the previous step. So that concludes problem 3 of problem set 2. Hopefully that was a helpful video. Let me know if you have any other questions. Yeah, good luck.